So what we're going to be learning today, after we first go through one more time balancing an equation, but that's the first thing you have to do before you write something called complete ionic equations. We're going to write complete and net ionic equations. Okay, writing complete and net ionic equations. Before you can write complete or net ionic equations, you got to know you have ionic compounds in the equation. Okay, it's got to be. Now there are only, well, I guess you could say there's three kinds of equations that we do in this class where you have complete net ionic equations. Okay. The kinds of equations that we've learned about in this class, for which ionic equations can be written, double replacement, acid-base double replacement, and single replacement. So every one of those equations you wrote for the lab, where there was actually a reaction, we can write a complete ionic equation for it. Okay, thank you. And then you had some homework that you did, complete acid-base and double replacement reactions. Well, if a reaction occurs, then we can write an ionic equation. Now look, if there's no reaction, there's no ionic equation either. Okay? Well, there is, but we don't worry about it. Okay? We just say no reaction, don't go any further. Okay? So, let's take a look at this reaction for an example. There's a 2 there and a 2 there. Actually, you know what? Instead of silver, I need to replace that with another element. Let's do, let's see, what could I use instead of that? How about nickel sulfate instead? No, not nickel sulfate. Well, because I don't want to start with silver. That would make things a little bit more complex than I want to do. Okay. Let's use rubidium. It's an easy one to replace it with because I don't have to change out any subscripts or anything. If you want whiteout, you should bring your own. Really? I would not know anything about that. It grows on trees? Really? Good. Yeah, cool. You haven't found one of those trees? Oh. Alright. So, what we want to do is to, well, I'll go and give you the physical states for the starting amounts, okay? Alright, so What kind of equation or reaction are we going to have here? What classification would we assign to this? Double replacement. We've got two ionic compounds. You can also think of it as being two-part compounds. Okay? So rubidium, and this is a polyatomic ion. Once again, if you don't know there's a polyatomic ion there, when you look at it, then what you want to do is look and say, I have 1, 2, 3 elements. If I have 3 elements, I'm going to go immediately to my common ions list and see if I can find some part of that formula that looks like one of these ions. If you're not using those test references in that way, you're like, I don't know, hammering nails with your forehead. Okay? Yeah, that would not be good. That would be bloody awful, wouldn't it? Literally bloody awful. Okay? Yeah. That was kind of the point. It was kind of a sort of joke. Okay. Well, anyway, the point is, why not use the test references? Why do you want to just guess? It doesn't work that way. Okay? I don't expect you to memorize all these ions. I want you to look them up. The more you use them, the more you're going to remember them. Okay? All right. And the same would be true here. Now, in this case, there's kind of a clue that we've got a polyatomic ion because the polyatomic ion is in a parentheses. Okay? The only reason we use parentheses is to show that we have more than one polyatomic ion. All right, so if it's double replacement, what's going to happen? If there's going to be a reaction, what's going to happen?
They're going to swap.
Yeah, we're going to swap. The front part of this compound joins up with the back part of this one. Okay? So we're going to put rubidium and nitrate, just going to lay them together over here. Doesn't mean it's balanced yet. We're not going to try to balance it yet. Okay, we're just going to put a single rubidium and a single nitrate together. Just set them up there together. Okay? Notice this subscript did not travel over here. This subscript didn't travel. The only subscripts that travel, that's the term I use sometimes, are those that are actually part of a polyatomic ion. So this subscript 3 is part of the nitrate ion. If you didn't know that, you'd find it on the common ions. Okay, the sulfate, the 4 here on that sulfate, means there's 4 oxygens in a sulfate ion. It's going to travel, okay, because it's part of the formula for the polyatomic ion. So let's put the front part of this compound with the back part of this one. Okay? All right. We want to know if there's a driving force. In double replacement reactions, there are 3 driving forces, and those 3 are all have to do with what we're making over here, what's formed. We've got to form a gas, and we said in a CP chemistry class, we don't worry about gases. All right, we're not going to do that in this class. But I want you to know that it's one of the driving forces, but we're not going to use it in any equations. The formation of water. That doesn't mean that we have water around. Water is around because these 2 compounds are listed as aqueous. Therefore, they're dissolved in water. Therefore, there's water around. Okay? We're not interested here in whether water is around. We're interested in whether or not water is formed. And that means one of these formulas has to be HOH or H2O. And since there isn't any HOH or H2O, there's no water formed. And the last driving force is the formation of a solid. To figure out there's a formation of a solid, we've got to use another tool from our toolbox on our test references, and that's the solubility rules. Okay? We want to know if one of these 2 compounds that are reformed is a solid. In an aqueous environment, is it going to be a solid? Okay? Now that means you've got to know what these names are. It means you've got to use that common ions list sometimes. Okay? We already said this is nitrate. If you didn't know that was nitrate, how would you find it? You go find it on the common ions list. Okay? That's a nitrate. So we'll look through here and we say, oh, well, nitrate's the very first thing listed, and the solubility rules tell us it's soluble. Soluble means it will dissolve. If water is around, it is dissolved. And this aqueous on these 2 compounds tells us water is there someplace. This reaction is taking place in water. Okay? So we can list this one as aqueous. Well, aqueous means dissolved in water. That's not a solid. That doesn't give us a driving force. So we're going to look over here at this one. We're going to look for either lead or sulfate. And if you look carefully, you'll find sulfates listed in the soluble section. It says sulfates are soluble except for lead 2. So that means if sulfate, most sulfate compounds are going to be soluble. They'll be aqueous if there's water around, but not if the sulfate is bonded to lead 2. Well, is this lead 2 or lead 4? We got to figure it out. We'll go back over here, and we have a lead bonded with a nitrate. Actually, we have 2 nitrates. We need to know from that common ions list what the charge on the nitrate is. Can anybody tell me what the charge is? No. Nitrate has a 1 negative charge. Since we only have 1 lead in the formula, what charge do we have to assign to that lead in order to have a charge-balanced formula? As many negative charges as positive charges. A 2. So this is lead 2. The name lead 2 comes from the charge on a metal that has more than one potential oxidation number. Okay? Lead, the Roman numeral 2 right here has nothing to do with the number of leads. It has to do with the charge on the lead. And this is a lead 2. Well, if it's lead 2 here, we can assume, at least for this equation, that it's lead 2 here. So sulfate is bonded to lead 2. It's not going to be aqueous because it's not soluble, we said, in the solubility rules. What do we write? Solid. Okay? So do we have a driving force? Yes, we have a driving force. Okay? Now, once we know we have a driving force, we're ready to balance the formulas. Okay? We need to know the charge on the rubidium. We already said nitrate has a 1 negative charge. What's the charge on the rubidium? Where would you find that? Well, the thing. Yeah, well, the thing is a movie. 1 plus. Rubidium is 1 plus over here on the. It's one of the alkali metals, and all the alkali metals have a 1 plus charge. So one of these and one of these charge balance. Okay, so we don't need any subscripts on this one. We said lead was going to be lead 2. What's the charge on the sulfate? 2 negative. Where did you find that? Common ions list, the polyatomic ions. And so that's a 2 plus and a 2 negative. That's already charge balanced. We don't need any subscripts to charge balance anything, so that's balanced. Now that the formulas are balanced, what are we going to do with those formulas? Are we going to change them? No. We can't touch this. Alright? Once the formulas are balanced, what? There you go. Alright. It was kind of weak. Probably didn't hear it on the video, but they said can't touch this. Alright, so now we're going to make an atom inventory. We're going to write down in a vertical fashion all the elements in these formulas. We have rubidium and sulfur and oxygen and lead and nitrogen. Okay? Oxygen is in 2 places, so we don't write it twice, we just write it once. So if you can work ahead, this would be a good chance for you to practice. Don't wait for me to do it for you. Go ahead and get it balanced. See if you can beat me to it. Well, you might. Because I'm sitting here talking about it and wasting time and chatting and, you know. 2 rubidiums. 1 sulfur. I have 4 oxygens here. 3 in the nitrate times 2 is 6. That's 10 oxygens. 1 lead and 2 outside this gives me 2 nitrogens. What? Oh, well then, let me get you some earplugs. Have Connor just reach up there and plug your ears for you while you do it. No, don't do that. Okay. It's just a joke. I wouldn't want you to do that anyway. Neither does he. Really?
Yep.
Yeah.
Sulfur balance. Lead.
I didn't say put it on the bottom. I said balance at last. I didn't say list at last. There you go. That's fine. You can list at last, but you don't have to. Just balance at last. How many of you beat me?
I did.
Good for you. Good for you. What do you mean get them together?
Like, I get the balances, but it's just before you get the balance your equation, that's what I don't know.
Before you get the balance in the formulas?
Yeah, like, figuring out what it is, and then
Oh, it just takes practice.
that's all.
And that's why we've been doing it for about 3 days now.
The problem like you did with number 7, I think what I need more practice on.
Okay? Well, you'll get more practice with these because we got to balance the equation, break the products and balance the equation before you can write ionic equations. Okay? So we're still practicing. We haven't gotten to it yet. I'm going to tell you right now. Now, what is an ionic equation? Since Connor asked. No, I was going to tell you anyway. All right. What we have here is these are ionic compounds. When they dissolve in water, they don't dissolve and just dissolve. They actually break up into separate ions. So all the rubidium ions actually separate in the water. And all the sulfate ions actually separate in the water. Okay? So in the water, since it is dissolved, if it's an ionic compound, and this only works for ionic compounds. Okay? Only ionic compounds break up in water.
So, if you get a water over there on the right side, so ionic compound?
Water doesn't break up. Well, you said if you get a water over here, if I made water H2O or HOH over here, it wouldn't break up because it's not ionic.
I know, but would it be
Okay, we'll do one of those, okay? Just be patient. So only ionic compounds break up when dissolved in water. All right, we got to make sure we have all ionic compounds, and all these are ionic, okay? Because all these happen to contain polyatomic ions. There are 2 tests for seeing if you have a polyatomic ion. An ionic compound rather. Okay, one of the tests is it a combination of a metal and nonmetal? Okay. The other one is, does it contain a polyatomic ion? If you have either one of those conditions, you've got an ionic compound. Now, it only breaks up if it's dissolved. Okay? It's got to have an AQ. It's got to be ionic, and it's got to have AQ after it. All right? So, this one over here doesn't have AQ after it. It's not going to break up. All these others are going to break up. So, when we balance this formula to start with, how many rubidium ions did we start with? 2. So we have 2 rubidium ions. We said those have a 1+ charge. This is dissolved, and it's dissolving the ionic compounds by breaking up the ions, so the ions dissolve. If the compound is aqueous, and if it's ionic, the ions are going to be aqueous. Okay? That's the way it breaks up. That's the way it dissolves. Huh? Such as rubidium.
So it's just rubidium?
No, we're going to do all the others too. How many sulfate ions do we have? 1. And you have to use not the separate sulfur and oxygen. It's the whole sulfate ion that is going to kind of hang together, but it's going to be separated from the rubidiums. We have just one of those. Okay? And here's lead 2, and we've already when we figured out what the charge on the lead was, we already pretty much broke that one up, didn't we? So that one kind of made it easy for us because we've already got it written out. The only thing we have to add to it is aqueous. We got 2 nitrates. We've already got this one broken up too. All right, but the only difference here is now we have 2 rubidiums and 2 nitrates because we had 2 of the whole compound. Oop, that should be R, then B. And then this last compound doesn't break up. We just write the way it is. If it doesn't break up, we just write it down like this. That's a complete ionic equation. It lists all the ions. I hope it's not hard. No. Why didn't I leave it like this? Because we want to see what's really going on, and eventually, if you take chemistry after this class, then you're going to need to be able to do redox equations, and this is a prerequisite for understanding how to do redox equations. In fact, most of the stuff that happens in the environment, or in fact an awful lot of stuff that happens in your body, is what you're really looking at are what the ions are doing and not what the equation's doing itself. So this is a complete ionic equation. Now it's important that you get the complete ionic equation right. If the complete ionic equation isn't right, you're not going to be able to get the net ionic equation right. The net ionic equation just simply gets rid of ions that are exactly the same on both sides. Okay? So let's look at this first ion right here. It's on the left side. I want to look and see if I have exactly the same kind and number of ions on the right side. Yeah. So we're not going to write that. Okay? We're just going to leave it out. Let's go to the next ion, sulfate. Do I have exactly the same kind and number of sulfate ions on the right side? No, because this is aqueous. It's separated. That one's not. So we're going to write sulfate. All right? I bet you can finish this out, sounds like. Can you finish it? Just write the ones that are not exactly the same on both sides. Say what? Yeah, should be. That's all there is to getting a net ionic equation. Yeah. If you get the complete ionic equation right, the net ionic equation should be pretty easy. You got to balance the formulas before the inventory. That's right. So MC Hammer didn't help you out on that one, huh? Okay. Sorry. How'd you do? Yep.
So the 2N of green has a negative charge on one side, it has a positive charge on one side.
Oh no, I'd have failed to put the charge on it.
Okay, that was my question.
Yep. That was just my oversight. Or overlooking, not oversight. I guess an oversight. I failed to notice. Anyway, okay? Alright, so this is then a net ionic equation. Okay, what do we call people that have to sit on the bench the whole game? Bench warmers. Okay. We don't call them bench warmers. Okay? We call them spectators in chemistry. And notice, these are the only things that are actually in the game. They're the only things that are actually changing. We got some things up here that aren't changing. Okay? Those are the spectator ions. Let's look and see if we can figure out what those are. So, the spectator ions rubidium. We didn't write it down here in our net ionic equation, so it's a spectator. Sulfate we wrote down, so it's not a spectator. Lead's in the game here. Nitrate's not in the game. So nitrate is a spectator ion. Okay? How are we doing? And these are players and these are spectators. All right. Ready to try one on your own? Okay, let's try one on your own. What's the... Oh, you didn't finish the notes yet? I can do it like this. And give you a practice problem like this right here. Actually, well, I want to give myself some room to do it, so... All right. All right now. All right. So to predict the products, then we're going to take the front part of this compound and put it with the back part of this one. This is acid base. You know this is acid because it's H on the front, base because it has OH on the back. These are arrhenius acids and bases. So the H is going to join up with the OH. You don't take this subscript over here and just stick it over there. The only time you move a subscript is when it's part of the formula for a polyatomic ion. This 3 is not part of the formula for a polyatomic ion. It tells you have 3 hydrogen ions. This is a hydroxide over here. The formula for hydroxide is OH. The subscript 2 just says I have 2 hydroxides. It's not part of the formula for the OH. So only the OH travels. Then the barium is going to move over here and join up with the phosphate. Okay? But we need to figure out if we have a driving force. Well, we already have a driving force in that we have water. But I still need to know what the physical state of this is. Okay? For that I use the solubility rules. And you'll see that most phosphates are insoluble. So even if there's water around, and there is water, aqueous means dissolved in water. This is the formula for water. There's water around, but still any kind of phosphates, with a couple of exceptions, I think if the phosphate is bonded with a group 1 metal or bonded with ammonium, that would make it aqueous. Okay? But since it's not bonded with one of those, this is going to be a solid. All right? Now we need to balance this formula. So barium, if you look it up on the periodic table with oxidation numbers, you'll see that barium has a 2+ charge when it's an ion. By the way, everything in that column, those are the alkali metals. The second column of the periodic table, all those are 2 pluses. Phosphate is 3 negative. You find that on the common ions list. So to charge balance this, I need 3 of these and 2 of these. This means I have 3 2 plus charges for a total of 6 plus charges, 2 3 negative charges for a total of 6 negative charges, and 6 plus charge balance is 6 negative. That makes sense? So to show that there are, in a formula that we have 3 bariums, I have a subscript 3 here. And to show that I have 2 phosphates, should have left some more room here. I put a subscript 2 here outside the parentheses. The only way to show that I have 2 phosphates and not 42 oxygens is to put a parentheses there. Okay? Now we're ready to balance the equation. So we're going to list all of our elements. We've got H, hydrogen and phosphorus, oxygen and barium. Do our atom inventory grid. So I have 5 hydrogens here and 2 outside the parentheses means I have 2 of everything inside, so I have 2 hydrogens. Keep up with it by putting it out here separately as math. 5 hydrogens. Is that what you started with? Good. 1 phosphorus. Okay. I've got oxygens in 2 places. I've got one here. I've got 4 oxygens. 2 outside the parentheses multiplies everything inside, so I've got 2 oxygens here. That's 6. And then I've got 1 barium. Over on the other side, I have 2 hydrogens. I have 2 outside the parentheses means I have 2 of everything inside. 1 phosphorus in the phosphate ion. 2 times 1 is 2. 2 phosphoruses. 4 oxygens in the formula for phosphate times 2 is 8. Let's do the math here. Keep up with it. I've got 1 oxygen here. Make it look like a 1. Plus 8 is 9 oxygens. And then I have 3 bariums, right? Alright, to balance this then, I need to start with oxygen's always going to be last and hydrogen next to last. I can start with the phosphorus here. I've got 1 phosphorus on the left and 2 on the right. To get 2 phosphoruses, I'll put a coefficient 2 in front of the whole formula. And that changes the number of hydrogens and phosphorus and oxygen. So now I have, let's do the math, hydrogens. I have 3 hydrogens times 2 is 6. 1 hydrogen times 2 is 2. Got 8 hydrogens. Okay? I have now 2 phosphoruses. This coefficient 2 applies to everything in the formula, so I've got 2 phosphoruses balancing those out. I now have 2 times 4 or 8 oxygens here, plus the 2 over here. So I've got 10 oxygens. Okay? Alright, so I've got the phosphoruses balanced. I'm going to save oxygen for last and hydrogen next to last. I need to balance barium next. I have 3 on this side. I need to have 3 on this side. To do that, I'll put a 3 here. That's going to change the number of bariums. It's going to change the number of hydrogens and oxygens. So I've got 3 bariums now. Let's count the hydrogens. 2 times 3 is 6. I've got 2 hydrogens. Because there's 2 outside the parentheses gives me 2 hydrogens times 3. That gives me 6 hydrogens. That's 12. Let's see, in oxygens, 2 times 4 is 8. 2 times 3 is 6. So I've got 14 oxygens. Okay, so barium's balanced, phosphorus is balanced, oxygen we're going to save for last, hydrogen we need to do next. I have 12 on the left, 2 on the right. To get a total of 12, I need a coefficient of 6 in front of that water formula. That's going to change the hydrogens and oxygens. So I only have hydrogen in this formula. I have 2 of them. Times 6 is 12. So oxygens I have 6 times 1 is 6. Plus 4 times 2, 8. So that's 14. And both sides of the equation are balanced. Okay? So the equation is balanced. Now we're ready to write the complete ionic equation. We're going to break this up completely because it's aqueous. And we treat acids like ionic compounds. Okay? They're going to break up. They're aqueous. So how many hydrogen ions do I have? 6 hydrogen ions. 3 times 2 is 6 hydrogen ions. And because the compound is aqueous, this is aqueous. How many phosphate ions do I have? PO4. And we said it was 3 negative over here already. And since the compound is aqueous, this is aqueous. Alright. This is aqueous. It's ionic. I've got a polyatomic ion telling me it's ionic. I have 3 bariums. We said barium has a 2 plus charge over here. Since the compound is aqueous, this is aqueous. And I have 2 hydroxides in the formula times 3, so I've got 6 hydroxides. Alright? Over on the other side of the equation, then, this is not going to break up because it's not aqueous. So 6HOH, liquid. And this is solid, so it's not going to break up. I'm going to have just 1 barium phosphate. Okay? So that's a complete ionic equation. This way a little bit. Okay? Alright, so there's nothing that's exactly the same on both sides. Alright? The hydrogen ion over here is not like the hydrogen that's bonded to the water. Okay? This phosphate's not like this one because this is a solid. It didn't break up into ions. Nothing on this side is exactly like this side. Therefore, this is both the net and complete ionic equation.
So you asked for a net.
Well, that is the net.
I know, but like if we have to do something like that,
Uh-huh.
we just like leave it blank.
No, you just say it's the same or something. Okay? Somehow you tell me you know that it's exactly the same. Alright? Fair enough? Hmm?
Draw arrows.
I suppose you could, depending on what the context is. Sure. Alright, let's practice another one. What do you say? Huh? Please? Okay. I don't know, can you? Alright, finish this one, please. And if there are net and complete ionic equations, write those.